Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome. So it's my pleasure to introduce Yanlei Diao. She's a PhD candidate at UC Berkeley, working under the supervision of Mike Franklin. And today she's going to talk about some recent work that she's done on XML Message Brokering. Okay, Yanlei.
All right, thank you. All right, testing. Okay, so today I will present my work on query processing for large-scale XML message brokering. Distributed information systems usually contain three abstract layers: presentation to the client at the bottom, resource management at the bottom, and then the middleware layer where the integration of different systems takes place. Traditional middleware infrastructures are tightly coupled. Systems built in a tightly coupled way are inflexible and brittle. Tight coupling can happen at two different levels. At a communication level, a tightly coupled system uses static point-to-point connections. This doesn't scale to larger systems where senders and receivers are constantly changing. Tight coupling can also happen at the content level, often in cases of remote database access. In order to access a database, application needs to know the structure of the database and its internal data types. This information is called database schema. In addition, applications break when the database schema evolves. So it has become very clear that tight coupling is inappropriate for modern internet-based applications. So now the industry is taking tremendous effort to solve the problem. So almost all information systems now support web services, a way to expose the functionality of information systems through standard web technologies. Then to glue different systems together, vendors of information infrastructure products are providing various solutions. For example, Cisco is moving up from the application level to support, from the network level to support application-oriented networking. And in the center of the messaging world, IBM MQ series provides advanced messaging platforms. And then from the database side, Oracle database is adding advanced queuing to the Oracle database. And application integration toolkits have been also designed by Microsoft and BEA systems. So as you can see, there has been tremendous effort to solve the problem. And in the vast space of distributed information systems, I focus on a particular component called the message-based middleware. So my work is based on two technology trends. The first one is the publish-subscribe interaction model. So in this model, subscribers express their interest in particular data items and are subsequently notified of the data items generated by the publishers. So PubSub provides a rendezvous-based mechanism that connects senders and receivers based on receivers' data interests. So PubSub has been accepted as a solution for the loose coupling of systems at a communication level. With respect to the content level, XML is becoming a de facto standard for online data exchange. XML is suitable for representing a common data format that senders and receivers agree upon because XML is flexible, extensible, and XML data is self-describing. In addition, XML can be used to provide enhanced functionality such as supporting SSLT for transformation and supporting an XML query language such as XQuery. So XML is gaining acceptance as a solution for the loose coupling at the content level. So these two trends lead to XML message brokering, the approach I take in my research to develop large-scale distributed systems. So XML message brokering integrates PubSub and XML to provide flexibility at both communication and content levels. In addition, it exploits declarative XML queries for added functionality. In the next slide, I will present a high-level overview of XML message brokering. So here's the broker, and then there are three clients. They subscribe by describing their data interests. And those subscriptions are stored as continuous queries that will be applied to all the data coming in the future. On the other hand, this broker is connected with a number of data sources. Those data sources publish data by simply pushing XML messages to the broker. Inside the broker, those messages are processed against all those queries one at a time, and the query results are delivered to the relevant clients. So such message brokering happens in a very dynamic environment. When a client comes, new client comes, it subscribes, and a new query gets added, and then the system starts to return results right away. When a new data source comes, it joins the system by simply pushing more messages, and that will increase the volume of messages inside the broker as well as the volume of results delivered. Okay, now let's take a closer look at how a message is processed inside the system. So this message is matched against all the queries. And in this example, query 1 and 3 are matched. For those queries that are not matched, this message is simply filtered out. So the first function is called filtering. And then customized results are created for each matched query. For example, the result for query 1 contains 2 fragments extracted from the input message. And then the result for query 3 contains 1 fragment extracted from the input. So the second function is called transformation. That is provided to create customized result delivery, customized results. And so far, I have described filtering and transformation in the setting of a single server. But the message brokering can be also provided by a network of brokers. So in that scenario, the third function is to route messages from where they enter the system to where the relative queries are. So the third function is called routing. Okay, so message brokering can be used to support a large number of applications. The first one is called application integration. Let me show you one example here. Those buyers generate requests for price quotation. And then this message broker integrates buyers with a large number of suppliers such that the best price can be found for each item in the request. Along the request flow, this broker forwards requests only to relevant suppliers. And if those suppliers are legacy systems and they use a different data format, this broker also transforms the request according to the requirements of specific suppliers. To do so, those suppliers provide queries describing the categories of items they support and then how the request should be transformed. And this is exactly what a message broker can do for them. The second example is called the personalized newspaper generation. This adds the personalization component to the current RSS feeds. For example, MSDN supports RSS feeds to deliver technical reports. And then there are other applications such as stock tickers, network monitoring, and mobile services. They can all benefit from XML message brokering. Okay, now let me take a minute to precisely define the problem I'm addressing in my work. There are 2 sets of inputs to message brokers. The first one is a continuously arriving XML message. The first input consists of messages. And in common cases, messages are fairly small. They're from 1 to 20 kilobytes. And then the other input is a set of queries representing client interests. And in my work, queries are written in a subset of X query. Now, given a stream of messages and a set of queries, XML message brokers provide 3 functions: filtering, transformation, and routing, as I explained in the previous slide. So the challenges lie in the fact that this functionality needs to be provided for large numbers of queries, for example, tens of thousands of them, and high volumes of XML messages, for example, tens up to hundreds per second. Okay, so I've described the problem, and now let me present the design space of XML message brokering and describe the position of my work in relation to other work. So this diagram consists of 2 dimensions. One is the style of processing. I consider centralized and distributed processing. The other dimension is the expressiveness that is determined by the data model and the query language. From the least expressive to the most expressive, there are 4 main categories. The first category is subject-based. So there, the data, actually the message is labeled with a subject by the publisher, and the queries usually contain 1 subject. The query answers yes or no, indicating if a message has matched the query. And the most commercial pub/sub systems fall into this category. Most of them also support distributed computing. The second category is predicate-based. So now the data contains attribute value pairs, and the queries can contain a conjunctive set of predicates. A predicate is a comparison between an attribute and a constant using equal, greater than, less than operators. There have been a number of research projects that support both centralized and distributed computing. The third category is called XML filtering. Now the data contains a hierarchical structure and it supports a much richer data model. And the queries are written in a subset of XML query language for filtering. We're going to see lots of examples in this talk. As you can see, many solutions have been developed in this category. So the solutions developed in the database community focus on the processing of a set of queries using optimizations. My work started from here. I developed an approach called the YFilter that supports a large set of filtering queries by exploiting commonalities. And then the solutions developed from the networking community focus on networking issues such as K-resilience in order of delivery, but they handle queries one at a time. The last category extends the previous one by also transforming messages for customized result delivery. So in the second piece of my work, I extended the YFilter to also support transformation for a large set of queries. This is the first algorithm in the literature that can do so on a large scale. And in the third piece of my work, I extended YFilter into a distributed system called Onyx. Onyx integrates the rich functionality of filtering and transformation into distributed computing, thus getting all the benefits of distributed computing. Okay, now let me summarize the contributions of my thesis work. I developed the YFilter, a system for XML filtering and transformation. For filtering, YFilter supports the shared processing of those filtering queries. By doing so, it provides order of magnitude performance benefits over previous work. It's highly scalable, up to hundreds of thousands of distinct queries. And I released YFilter 1.0. It's open source software system for filtering. Has been used in research projects for grid monitoring for event processing, has been re-implemented by Cisco, and Apache Hermes has integrated YFilter into their package for web service notification. So transformation for lots of queries was previous unaddressed problem. My algorithm is the first in the literature that can transform for a large set of queries, and algorithm scales up to tens of thousands of distinct queries. And in the third piece of my work, I'm developing a distributed system called Onyx. It's an overlay network of brokers with routing capabilities. So Onyx is designed to provide flexible internet-scale XML dissemination services. Okay, I have described the problem and provided background. So in the rest of my talk, I will focus on the second issue called XML transformation. So transformation is important for application integration for personalization. But transformation for lots of queries was previously unaddressed problem. So my solution leverages my prior work for filtering and maps the problem of transformation from the relational setting, from the XML setting to the relational setting for high performance processing. If time permits, I'll also provide an overview of XML routing and conclude my talk. Okay, now let me say more about transformation. So this is the broker with two transformation queries. And the first query extracts interesting sections from a technical report, such as MSD and technical report. And then this query looks for interesting sections. It says for each section whose difficulty level is easy, if its title pops up and it contains a figure whose title is XML processing, return a new section to contain all the titles of subsections and all the figures. So this query can be written in a subset of X query, the for-where return expression. The for clause creates an ordered sequence of bindings of sections to a variable $s. The where clause filters those bindings by checking additional predicates. And then the return clause is invoked once for each binding. In the invocation, it can create strings using constant tags. It can also extract additional content from the current binding by using those path structures. And the final result of this query is an ordered sequence of those return clause invocations. As we can see, the important components of this query are those path structures called path expressions. So the for-where return expression stitches those path expressions to create bindings and final results. I will say more about path expressions in a minute. Okay, the second query is a different query, but it uses a similar for-where return structure to extract interesting sections. The one that technical report comes, if it matches both queries, two different results will be created. To do so, a simple solution is to iterate over the query set and handle queries one at a time. But this doesn't scale given our goal to support transformation for thousands of queries. If we take a closer look at those two queries, we see actually they share pieces together. For example, the two for clauses share the expression /section, and the two where clauses share the same predicate. And even the where and the return clause can share the same path/title. So the goal of this piece of work is to identify such commonalities among queries and the shared processing for efficiency and the scalability. Okay, now let me say more about path expressions, since they are the major components of transformation queries. Let me start with a document. This is a technical report, has a hierarchical structure, has one root element and nested elements. So the root is report. It has a child element section, and this section contains a title, a nested section, and a figure. An XML element starts with the start tag, optional with some attributes, and end with an end tag. In addition to sub-elements, an element can also contain text data. So a general set of rules for such attributes and elements can be provided by a document type definition DTD or a schema. But the knowledge that a document conforms to DTD or schema is optional. So I do not require this information for query processing, but I can exploit it for optimization when this information is indeed available. And this document can be naturally represented as a node labeled tree inside the system. So one node corresponds to one element. A node can contain child nodes, and a node is also annotated with attributes and text data. Finally, node IDs are assigned according to a pre-ordered traversal of the tree. That's all we need to know about XML representation. Okay, now let me talk about path expressions. So the first path, it starts with a variable $doc referring to the current input message. And that's followed by 3 steps. Those 3 steps say that the root is a report, and the report contains a child element section. And there's a value-based predicate here requiring attribute difficulty to have value easy. And such section should contain child element title. So this path can be matched by the 3 highlighted nodes, and it will return the title as the result. Let's look at another example. Now this path contains a descendant operator represented by /. So this operator says section and the title can be separated by any level of element nesting in between. For example, this path can be matched by these 5 highlighted nodes, and it will return all 3 titles as the result. So in summary, a path expression is a sequence of steps called location steps. And the location step starts with the child or descendant operator, followed by an element name or wildcard that can match any element name, followed by an arbitrary sequence of value-based predicates. Next, let me summarize the filtering solution. The filtering problem is to efficiently match a large set of path expressions. In YFilter, I support shared processing of path expressions. So YFilter exploits common prefixes among path expressions, and it uses a non-deterministic finite automaton-based model. So these are the 2 paths we have seen. Given some other paths, YFilter merges all of them into a single combined NFA to exploit the common prefixes. By doing so, YFilter is order of magnitude faster than solutions that do not share the processing or only share the processing in a limited way, and is highly scalable. Finally, it only requires a small maintenance cost when the queries are updated. So there are lots of technical details. You're encouraged to read my paper, Path Sharing and the Predicate Evaluation for High Performance XML Filtering, and it was published in XML Transactions on Database Systems, December 2003. Okay, so I've told you 2 things. First, path expressions are core components of transformation queries. Second, shared processing is crucial for performance. So next, I'd like to develop the transformation functionality on top of shared path matching. Let me start with the transformation architecture. So this is the YFilter system. The main input consists of XML messages. For each input message, a number of customized messages can be output. Another input consists of queries, but queries arrive at a much lower rate than messages. At the core of YFilter, there's a query processor. It contains a compiler and a runtime system. When a query comes, it's parsed and sent to the query compiler. The compiler creates a query plan and merges with a global pool of shared query plans. This data structure contains NFA to represent a set of path expressions and operator network that handles the remainders of those queries with certain path expressions taken out. At runtime, when a message comes, it's run through an event-based parser. So this parser breaks hierarchical structure into a linear sequence of events such as start of element, text data, and end of element. And those events are materialized into a node-labeled tree for the use of query processing. They also use to drive the execution of a runtime system. And inside the runtime system, the events are used to drive the execution of a shared path matching engine that runs this NFA. And then path matching results in output in the format called path tuple streams. They're directed into a transformation module that executes this operator network. Sometimes it also accesses the node-labeled tree. And the query processing results in output in intermediate format. They're directed into the message factory where the final messages are prepared for delivery. So the contributions of YFilter contain this blue area for shared matching of path expressions and the red area for transformation. In this talk, I will treat the blue area as a black box, and I'll focus on the red area for transformation. Okay, so in order to develop the transformation module, there are two fundamental questions to address. First, is the transformation operations navigational or relational? So most XML processing uses tree-based navigational operations, but there has been 30 years of work for high-performance relational processing. Can we leverage the relational processing in this new context? The second question is, to what extent can shared path matching be exploited? Potentially various degrees of path sharing are possible, but how do we choose the right transformation operations to reconstruct complex relationships? It turns out the hard part of this work is that many choices available with respect to these two issues, but only a few can scale to large-scale query processing. Query optimization as such is a well-known hard problem in the database literature because many solutions introduce overhead in order to share the processing, and overhead can dominate the benefit of sharing with increased query workloads. Given my scale of processing, I really need solutions that exploit significant sharing, but with overhead as little as possible. So in the next few slides, I will provide answers to these two questions and show you how solutions can be developed in a principled way. Okay, the answer to the first question, can we leverage relational processing, is yes. And the answer is based on the use of path tuple streams. So let me explain path tuple streams through examples. There are two paths in the system. The first one looks for figures inside some section. The second path looks for figures whose parent section is in another section. And the shared representation is contained in this shared path matching engine. And you don't have to worry about details here. And then this is a technical report we have seen. So parsing events are created in order of pre-order traversal of this tree. Excuse me. And then parsing events are used to drive the execution of the shared path matching engine. Excuse me. And when parsing reaches node 5, now both paths are matched. So this engine creates two path tuple streams. In the first stream, the first tuple says node 2 and 5 match this path. The second tuple says node 4 and 5 match this path. In the second stream, this tuple says node 2, 4, 5 match this path. And then when parsing reaches node 7, a new tuple is created and appended to the first stream. This tuple says node 2 and 7 also match this path. So in summary, this engine creates a stream for each matched path expression. And the path tuple represents a unique match of the path with one field per location step. And the value of the field is the ID of the node that matches this location step. An important property of a stream is ordering. So path tuples in a stream are created in the way that node IDs in the last field in monotonic or increasing order. So this ordering can be exploited for XML transformation where the ordering of results matters. Then here's my answer. By creating those path tuple streams, now transformation becomes operations on those path tuple streams. That allows me to use relational operators and optimization techniques in this new context. So different from other researchers who propose holistic query pattern matching, the fundamental approach I take is to create path tuple streams and leverage the relational techniques people developed in the past 30 years because we understand processing and optimization much better. The second issue is what degree of path sharing can be exploited. Now, let me go back to these two example queries. Given my architecture, I have two choices. I can take all those paths and insert them down to the shared path matching engine. But it's important to know that those where and return paths are relative to variable $s. That means they're relative to the paths in the for clause. But this shared path matching engine treats all paths as independent in order to use this NFA-based model for shared processing. To bridge the gap, what I can do is to pre-append those where and return paths using the for paths. So basically, I make all the paths absolute, and then I insert them down to the engine. In this way, I can share the processing among paths both within a query and across queries. But by making those paths shareable, I have departed from original query semantics by ignoring correlations among paths. So it turns out I need to do more in the transformation module to reestablish the correlations among paths. That's certainly the overhead of this algorithm. Alternatively, I can stay loyal to the original queries and then leave all the relative paths to the transformation module. In this way, I don't get much benefit of shared processing, but I don't have to pay for the overhead. So the issue is, which way should I choose? So given the trade-off between the benefit of path sharing and the overhead of path sharing, I developed a family of algorithms that differ in the extent of path sharing. So next, I'd like to present the most aggressive approach in terms of path sharing, called path sharing FWR. It shares paths from for, where, and return clauses across all queries. So this is our query 1. And given the shared path matching engine, I will extract all the path expressions without value-based comparisons. I prepend them if necessary and insert all of them down to the engine. At runtime, a collection of path tuple streams will be output. So the thick arrows denote the ones that will be used for this query. From left to right, the first stream is for the for path, the next two streams are for the two where path, and the last two streams are for the two return paths. And those streams are directed into an external query plan that processes the remainder of this query. So I create an external plan for each query and I call it a post-processing plan. So constructing post-processing plans is analogous to how relational systems such as SQL Server and Oracle compile SQL queries, but the choices of operators are different here. From bottom up, this plan can contain the following operators. Selection performs value-based comparison. For example, I use the selection to handle this value-based comparison applied to the for path. And after that, projection. It projects path tuples onto specific fields and removes duplicates. So there's some engineering detail here. I will explain it in a second. These two operators completely process the for clause. And again, I use selection to handle value-based comparisons applied to those where paths. After that, I use a left deep tree of semi-join operators to handle the correlations between the for and the where paths and to find query matches. And up here, for and where clauses have been completely processed. Again, I apply projections onto those return paths. And finally, I use an outer join operator to handle the correlations among for and return paths and create results. So in the next two slides, I will explain those operators in more detail. Okay, so this is query 1. This is the query plan. So those operators can be formally defined at algebraic level. In this talk, I will not provide a formal definition. Instead, I will illustrate their execution through an example. So this is a technical report extending the one I've shown you. Given this report, path tuple streams are created. I annotate those streams using their corresponding path expressions. And the red parts denote the last common field among path expressions. This field is called the binding field. In this example, the binding field is the section field. Okay, now let's look at the for path stream first. This stream carries sections identified from the technical report. And they are passed to a selection operator checking this value-based comparison against sections. And only output sections that match this predicate. And then this stream is directed to a projection operator. It projects the stream onto the binding field and removes duplicates. So this operator makes sure that we do not create duplicate bindings. And in this example, duplicates simply do not occur. Now let's look at the where path streams. Assume they have already passed their corresponding selection operators. I use two cascading semi-joins to find query matches that are sections matching both where paths in this example. So the first semi-join takes the 4-path stream as the left input and the stream for the first where path as the right input. And the join is performed on the binding field, and the output sections, each one of them has a match from the right input. So in this example, node 4 is filtered out because it doesn't have a match from the right input. So similarly, the second semi-join merges the 4-path stream with the second where path stream, and only output sections that also match the second where path. Okay, now let's quickly look at the return path stream. So first, apply projection onto this return path stream. This operator makes sure that for each binding, only distinct nodes are selected for each return path. So in this example, for binding node 2, actually there are 2 duplicate title nodes. So I use a projection to project the stream onto the binding field and the return field, the last field, and removes duplicates. So similarly, I use a projection onto the second return path stream. So last, let's look at outer join. In my work, I use an n-way specialized outer join called outer join select. It takes the 4-path stream as the left input and n-1 return path streams, and it creates results directly. So one group corresponds to one 4-path tuple, and the group contains join results between this tuple and those return path streams. For example, the join between node 2 and this first return path stream finds 3 matches, and extracts the node IDs from the last field title and places them into a list. The join between node 2 and the second stream finds 2 matches, so extracts the node IDs from last field figure and places them into the second list. So the processing for the second tuple is similar, except that the join between node 13 and the first return path stream doesn't find any matches, so it creates an empty list. If you're familiar with the database literature, the semantics is exactly what outer join carries. So do you have a question?
If I have a question, in the query, if I had, instead of the first word clause, I had $s/less title. So how will the number of paths change here? Or will it be the same?
Number of paths?
Yeah. If it was $s/less title, which means within $s, the title could be anywhere, any level T, right? Then how will the number of paths, will it remain the same, the path streams which you have? Or how will the processing change here?
First I'd like to clarify that there are 5 streams here. They correspond to these 5 paths. So even if I change the operator from child to descendant, I still have 5 paths. And then what differs is the tuples that are in the stream might change when I change the operators. But the processing paradigm stays the same. Actually, even the query plan stays the same. Just the number of tuples you see in the stream might differ.
Yeah, that would have been my next question. How would you, the tuples, how will the number change? Because that could change a lot, right?
Right. Actually, when I present the performance study, I would tell you there are a number of parameters we can tune to control the system, and I'll tell you what we observe by changing different parameters. So why don't we just hold it for a minute? Okay, so I've told you what those operators do. For efficient processing, physical implementations of those operators are very important. In this slide, I will talk about some of them. So I will focus on semi-join. I'm showing those path-tuple streams surrounding semi-joins. So first, the semi-join preserved order from the left input. So that means the order of the 4-path stream can be preserved all the way to the output for the correct results. Second, I have 2 versions of implementations. First, I have a hash-based implementation. It works in all scenarios. Given a hash function, it creates a hash table from the right input and applies the same hash function to the left input and uses hash values to probe the hash table to find all matches. In some scenarios, when the 2 streams are already ordered by the binding field, a cheaper merge-based implementation can be used. There, I simply merge these 2 streams to find matches. If you look at the first semi-join, actually both streams are already ordered by the binding field. So the cheap merge-based implementation is enough. But if you look at the second semi-join, this word path stream is not ordered by the binding field. So the more expensive hash-based implementation is needed. Because hashing is more expensive, it turns out hash-based join implementation is a major source of overhead of this algorithm. And implementation issues for outer joins are similar. I'd like to mention that when outer joins implemented using hashing, it's another source of overhead in this algorithm. So finally, implementation choices also exist for projection. So projection on the 4 paths is defined on the last field, and the tuples are already ordered by the last field, so a simple scan is enough to implement projection. But projection on the return path stream is defined on 2 fields, so ordering the last field now doesn't always guarantee a cheap implementation. I like to omit the technical details here, but just like to mention that projections on the return path streams are another potential source of overhead in this algorithm. So, what I've told you is that there's certain overhead in this most aggressive path sharing algorithm when it tries to identify the correlations among paths. To reduce the overhead, I have other algorithms that exploit path sharing less. This
This is for different queries with different structures. And if you have different queries with exactly the same structure but just different constants, then
yeah, I will capture that in the third step of this work. So currently I'm still deriving the query plans. The next step, I will simplify the plans. The third step, I will also merge query plans across queries. Okay, I will come to that. Okay, so the second algorithm, I only share paths from for and where clauses across all queries. So this is the query plan for FWR. So what I do is I replace those operators for those return paths and replace them using a single operator called return select. Return select applies the return clause without sharing. It's invoked for each input path tuple. And during the invocation, it evaluates return paths one at a time using a tree search-based routine. So basically, I just navigate in this node label representation to find matches of each return path. This is no longer a relational operator. And the last algorithm is called path sharing F. It shares paths from 4 clauses across all queries. So this is planned for FW. I further remove operators that handle those where paths and replace them using a single operator called where test. Where test tests predicates in a where clause without sharing. Similarly, it's invoked once for each input path tuple and evaluates where paths one at a time using tree search-based routine. So I have told you there are 3 algorithms that differ in the extent of path sharing. Due to the trade-off between overhead and benefit of path sharing, the 3 algorithms have different performance characteristics. So I implemented all 3 algorithms in Java and I compared them through a performance study. So all the experiments were run on a Pentium 3 850 MHz processor. It's a pretty old desktop. And I used JVM 1.3. The Java allocation pool was set to 600 megabytes. It's smaller than the size of the physical memory. I tested algorithms in different domains. I used the bibliography and technical report DTDs from the W3C xQuery use cases. I also used a news industry text format DTD. This is the one that a lot of publishers are using to publish articles online. And then to test those algorithms, I created a document generator. Given a DTD, it creates a set of XML documents. I also created a query generator based on probabilistic model. So given a DTD and a set of parameters, it creates a set of distinct queries. So in this work, I used a uniform distribution to generate random distinct queries. And those are most challenging workloads with respect to the amount of commonality that can be exploited by my algorithms. And the performance metric is called multi-query processing time. It's the wall clock time of processing all queries, excluding parsing. On this processor, parsing usually takes less than 10 milliseconds. And all the numbers I report were averaged over 180 documents. Okay, in the first experiment, I compared 3 algorithms using non-recursive data. Non-recursive means an element cannot contain another element with the same name in it. So this is the simplest data format you can find. And the effect of recursion is the focus of a later study. So first, I used the bibliography DTD. The data contains 4 levels of element nesting. This is actually the maximum this DTD allows. On average, each document contains 20 books, and each book contains information on the publisher, the authors, and the price, etc. The size of the domain where attributes can take values from is set to 10. So this determines how selective value-based predicates can be. And I created 5,000 queries each query contains 1 word path, 2 return paths, and the maximum depth of the 4 paths is set to 2. The maximum depth of the word and return path is also set to 2. Finally, the probability of a descendant operator per location step is set to 0.2. So this is a fairly large probability for those descendant operators. Okay, here are the main results. So the 3 bars from left to right are for the least path sharing to the most path sharing. So it's interesting to see that the second algorithm actually performs the best, and the most aggressive path sharing algorithm performs the worst. To understand the results, I'm also showing you the cost of individual operators. It turns out FW outperforms F due to sheer processing of a word path. It can be verified as follows. So F uses word tasks to handle word paths without sharing and takes 386 milliseconds. FW uses the shared path matching engine to match those word paths, and in addition uses selections and semi-joins. But the cost of the 3 operators is much less than word test. On the other hand, FWR is much worse than FW due to the high overhead in processing return paths. For example, FW uses return select to handle return paths without sharing, and it takes 212 milliseconds. FWR uses projection on the return path streams and outer joins, but the cost of these 2 operators is much higher than no sharing at all. So far, the biggest observation has been aggressive path sharing can lead to high overhead processing plans. And the overhead comes from hash-based join implementations and projection with duplicate elimination. So in the next step of this work, I developed optimizations based on query and DTD inspection. So I try to turn hash-based joins to merge-based joins if possible, and I try to remove unnecessary duplicate elimination from projections. So those optimizations provided by using sufficient conditions that can be proved correct. For example, for semi-join and outer join, I have sufficient conditions that check when the word and return path streams are altered by the binding field, so that I can use the cheap merge-based implementation. And those sufficient conditions are based on observation that certain combinations of recursive data and descendant operators will make those streams out of order. So the theoretical side of this work is a very important contribution of this work. In this talk, I do not have time to explain those results, but I'd like to mention that one condition is based on query inspection only. It looks for descendant operators in certain places in the query. The other condition is based on query and DTD inspection. It looks for descendant operators. It also checks if DTD allows certain elements to be recursive. And similarly, I have conditions to remove unnecessary duplicate elimination. Okay, in the next experiment, I compare 3 algorithms, including optimizations. So the experimental setting stays the same. And here are the results. So now there are 3 groups of bars. The first group is for no optimizations that I've explained. The second group is for using query-based optimizations. And the third group is for using query and DTD-based optimizations. As we can see, when query-based optimizations are applied, all 3 algorithms improve their performance. But the most aggressive algorithm improves the most and starts to outperform others. When DTD-based optimizations are further applied, the most aggressive approach outperforms others by a wide margin. To understand the improvements, I'm also showing the cost of individual operators. As we can see, so as optimizations are applied, projection, semi-join, and outer join improve their performance the most. When query-based optimizations are applied, the most cost of projection actually is avoided, and the cost of semi-join and outer join are halved. When DTD-based optimizations are further applied, the cost of projections are completely avoided, and the cost of semi-join and outer join kept low. It turns out our optimizations are very effective for non-recursive data. Basically, we can eliminate all duplicate elimination and turn all hash-based to merge-based joins. But then what happens when the data is recursive? In the next experiment, I used recursive data. So I went back to the technical report DTD. So now the data contains 5 levels of element nesting. And on the average, each document contains 12 top-level sections. Each section contains up to 4 nested sections, and this goes on until the data reaches level 5. So it's deeply recursive data. And I created 10,000 queries and the maximum depth of the forward pass is increased to 3, other parameters stay the same. So here are the results. So you can observe similar trends, except that when query-based optimization is applied, the most aggressive algorithm is still worse than FW. So when DTD-based optimizations are further applied, so FWR finally becomes the best, but it's only slightly better. So I do not have time to show the cost breakdown in this talk, but I'd like to mention that when the data is recursive and there are many descendant operators, there are many join operators where the join order is not guaranteed. So I have to use hash-based implementation. So that means these two things limit the effectiveness of DTD-based optimizations. And I performed many other experiments. For example, increased number of where paths. So with more where paths, queries become more selective. Then the performance of FW and FWR start to converge. And also vary the number of return paths. With more return paths, FWR outperforms others by even bigger margin because of shared processing of return paths. And also vary the descendant operator and use other DTD. Let me summarize those results. First, the best performing algorithm can handle thousands of queries in sub-second response time. Second, path-sharing FWR with query and DTD-based optimizations provides the best performance. The takeaway is that when the DTD is available, it's safe to use the most aggressive path-sharing algorithm. Then what happens when DTD is not available? I can either fall back to FW or I need to add adaptivity by using online learning algorithms. Those algorithms can learn from the past to predict the best performing algorithm for the current workload. So that's a very important direction for future work, integrating machine learning and query processing. And the last one is the effectiveness of optimizations is based on the information available to the optimizer. So DTD-based optimization is much more effective than query-based. Finally, recursive data and descendant operators limit this effectiveness. Okay, so far I have been using a separate post-processing plan per query. I want to further share the post-processing across queries. By using relational operators, my query plans are very similar to those for continuous query processing in the relational setting. So inspired by this, I developed a set of sharing techniques similar in spirit to continuous query processing, but they're highly tailored for XML Message Brokering. I do not have time to describe those techniques, but I'd like to mention that the best case scenarios show significant scalability improvements. For example, by using shared post-processing, I can process 20,000 queries in 40 milliseconds for bibliography and 130 milliseconds for technical report. But these are best case scenarios because now the sharing techniques only work for limited cases. So techniques for sharing post-processing will be expanded together with the development of continuous query processing in a relational setting. Last, let me take a minute to summarize my work on Onyx. So I've told you that YFilter can be used to provide services that disseminate data from data sources to the clients. In the third piece of my work, I split YFilter into a distributed system. It's a network of brokers. So the system is called Onyx. It stands for Operator Network Using YFilter for XML Dissemination. It's an overlay network of information brokers running YFilter. And then because it's an overlay network, it can be deployed on a variety of underlying infrastructures, including a dedicated network, a peer-to-peer system, or some sort of collaboration among different administrative domains. In this talk, I will summarize one key feature of Onyx called content-based routing. So Onyx consists of two layers, the network layer and the content layer. So the network layer constructs broadcast trees. For each broker, it creates a tree that connects its broker to other brokers in this system. And the content layer deals with queries and messages on top of the network layer. Let's look at queries first. So queries are placed onto a subset of brokers. And then we aggregate those queries to construct content-based routing tables. A content-based routing table summarizes the data interests of downstream brokers and can be implemented using the YFilter technology consisting of an NFA and an operator network. Okay, along the data flow, when a message comes, the content is extracted to do the content routing table lookup. So in this way, instead of sending messages along all upper links, I can send it to only a subset. And this is repeated at each broker until the message reaches all relevant brokers. So by doing so, we can avoid broadcasting messages in a massively distributed system. And then the name, we give it a name because this type of routing stands in sharp contrast to IP-based routing. And there are two main points in this piece of work. First, we can leverage YFilter to build content-based routers. Second, high-performance routing is provided by two key algorithms. The first one is query population partitioning. That is how we assign those queries to brokers. The second is query aggregation. That is, given a placement, how do we aggregate queries to construct those routing tables? So there are many details provided in my VLDB paper last year towards internet scale XML dissemination. Okay, now let me summarize my talk. So now the information industry is moving towards building large-scale, flexible, high-function distributed systems. XML-based PubSub emerges as the infrastructure that meets those requirements. And my work, including YFilter and Onyx, provides key components of this new infrastructure. For filtering, YFilter supports shared processing of past expressions. It's order of magnitude faster than previous work. The code has been released and has been fairly widely used. In the transformation, my algorithm is the first in the literature that it can handle tens of thousands of distinct queries. Finally, for routing, I'm currently developing high-performance content-based routers by leveraging the YFilter technology and adding new algorithms for query population partitioning and aggregation. In retrospect, there are three key ideas that I exploited in my research. First, sharing is key to performance and scalability. I apply sharing to filtering and transformation. Second, I can leverage relational techniques in the new context of XML processing. So recall that I create past-type streams and leverage relational techniques to better optimize transformation. The last one, queries bring intelligence to the network routing fabric. So my work on high-performance routing is one piece along the dimension where the networking systems and database systems or data management systems converge to solve the large-scale data dissemination problem. I just like to quickly mention my future work. So my thesis work has led to a number of interesting directions for future work. I like to continue with large-scale data dissemination and add a number of important services. For example, currently, messages are processed one at a time with no interaction across message boundaries. I like to add so-called stateful publish subscribe that allow data to be aggregated across a stream of messages. So doing this in a distributed environment is a very challenging issue because now we need to maintain a computation state across messages on a per query basis. Another one is access to historical data. So this is important to compare your observation now with your observation last week. And then how to do that in a distributed environment actually, again, is a very interesting issue. In addition, I'd like to add a quality of service-based publish subscribe to also take into account time-based constraints and a policy-based publish subscribe for security reasons. Okay, the second big dimension I'd like to pursue is complex event processing for sensor-based networks. So sensor devices are gaining acceptance in a growing number of applications for environment monitoring for supply chain management. And then the wide deployment of sensors will soon generate an unprecedented volume of events. Those events need to be filtered and combined to identify complex event patterns. They also need to be transformed along a concept hierarchy to create new events that reach the semantic level appropriate for end applications. In addition, along the way of transformation, data lineage is important to evaluate the quality of data for applications such as tornado prediction. So I've told you that distributed information systems are a rich area of interdisciplinary research. Personally, I'm interested in many new directions that require query processing technology for increased flexibility and functionality. And those directions include web services, data integration, and knowledge acquisition on the semantic web. Existing query processing technology needs to be extended and enriched to rise to the challenges of those new environments. And that's the end of my talk.
Okay. Any more questions? How does your technique scale with the number of queries? I mean, 10,000 doesn't strike me as a big number if you're talking about internet scale.
Yeah, so I do have a backup slide. So basically, the worst case is linear, right, with respect to number of queries. So what we can do is try to reduce the constants by sharing those operators across queries. And then in some restricted cases, we can also achieve sublinear performance. For example, if we only consider simple path expressions, in the first piece of filtering, we indeed gain the sublinear curve as the number of queries, distinct queries increases. So we're really trying to achieve this curve. If queries are too complex, then we try to reduce the constants. But there's still like a limit we can achieve within a single processor. So there, to further increase, we can either use parallel processing, so the plans can be easily parallelized, or when we move to distributed system, by using multiple brokers, that's another way to gain even higher scalability.
What about YFilter, though, in particular, without factoring out the X-query processing? I mean, is that... I've seen numbers out of the University of Washington that indicate basically insensitivity to the number of...
Right, I think you're like referring to Professor Dan Susho's work,
yeah,
right? Yeah. He converts NFA into a DFA, so basically that provides constant lookup time. But there are two big problems. One is the state. So basically, they experience exponential blow-up when the DTD is complex. For this news article, NITF-DD that I used, my system, I used like 50 megabytes, but they ran out of 2 gigabyte memory. They just couldn't store the machine in the memory. Another problem is query updates. So once you convert a machine to a deterministic one, whenever queries change, you have to reconstruct a big portion of the machine. So that's why their curve looks like a warm-up phase, high throughput, and a dramatic drop, and a warm-up again. So you experience those kind of curves. So I think the choices between the two systems totally depend on your application. If your queries don't change, they're fairly simple, you can afford to use DFA. But if you want to support other workloads, I think the NLP one is more robust, flexible. But certainly the best case throughput is not as high as that.
You started by saying you assume small XML messages. Mm-hmm. My instinct would be to skip the transformational step entirely and send the original XML messages to everyone who is interested.
I see. So your question is rather, why do I do transformation inside the middleware, right?
Yeah.
Okay, so there are a number of reasons. I think first is deployment. By asking the middleware to do the transformation, it's easy to deploy because if those clients are mobile users or other users, they don't even have to install X-query processor. So that means, they don't have to update their software changes. So this is a deployment argument. Another one is shared processing. By collecting all the queries inside my system, I can identify commonalities in the shared processing, so to cut down the total processing cost. The third one is flexibility. So once I move to a distributed system, I can even decide where I do the transformation. I can do it as early as possible to reduce the size of messages, or I can leave it all the way until the edge brokers where the final query processing is done. So I also gain this flexibility in my system. Okay?
So, coming back to my earlier question, I think your benchmark, your performance study used randomly generated queries, which could be different. Mm-hmm. So coming back to my question, if you had a few query templates with just different constants, mm-hmm. A, due to any indexing and such like to eliminate candidates, and B, on such a workload, would your performance result still look the same, or would it look better for sure?
So definitely the performance better. Actually, I didn't have time to explain for your workloads you mentioned. So my algorithm will catch it. What happens is that they have different selection operators, right? But they have the same join. In the third piece of sharing post-processing, I have a technique called, or I use the Niagara SQL technique called selection pull-up. I delay all the selections so they share the same join. So really, the last piece, we can catch a lot of similarity across query plans. We can even move relational operators around to increase sharing. So that's why it's great to map the XML transformation problem to SQL processing, that the two fields can be developed simultaneously.
Do you use any indexing on queries as opposed to the data?
So actually, the NFA and those shared query plan, you can think of as an index over all those queries, right? I guess what you say is index over constants of a particular, right? We do have that, but by using random distinct queries and a fairly complex schema, actually we don't see the benefit. I think your benefit appears when really queries are extremely similar, but they only differ in the constants. Yeah, we do have that technique. If that's a workload, we can catch it. Because this is a standard technique that SQL processing focuses on. Yeah.
So if you have indexes on your data, right, how will that change query processing? Will that change the construction of your NFA, or should it be insensitive to it?
Yeah, actually, so actually a lot of researchers have considered this. For example, Professor Dan Sucio, he constructs an index over data when it's, it's very long, and then if by analyzing queries, you can skip portion of the data. So that actually has been looked at by other groups. Because my workloads, messages are fairly small. They're only 1 to 20 kilobytes, and I have lots of queries. So the benefit by constructing index over data, skipping portion of it, is very limited. But it might be important for other workloads.
I think the tech report example is really a stream application. So, typically you have an archive of tech reports, and you could just use ordinary XQuery processing to figure out now which are the qualifying tech reports. I don't think that we get thousands of new tech reports every day or so on. So the question is, do you have also applied now your implementation to real applications with streaming requirements?
For example, I also use a news article, DTD. I use technical report because the data is highly recursive. It shows many aspects of query processing. But we intensively test our algorithms using news articles. As the results are pretty similar. The throughput it's close. So the specific trade-off between like the three algorithms are slightly different, but they really they fall between these two extremes of non-recursivity and deeply recursive data. So throughput is about 100 messages per second for tens of thousands distinct queries. That's the throughput we can achieve. Actually, NITF, it's fairly complex, but it's rather the amount of recursion that determines the throughput of my algorithm. So the recursion of the news article falls in between this bibliography, no recursion, and technical report, deeply recursive. So that's why I presented two extremes and say, the news article falls in between. But this functionality indeed has not been largely deployed, so we do not have real workloads available.
Last question.
Are there any theorems about maximal possible sharing or most efficient possible way of doing query matching?
We don't have theorems, but if you think of it, we can capture something that natural, for example, prefix sharing, and when we further share post-processing, we can even move operators around. So go back to the example I have. Two queries have different predicates, but they have the same structure. There, we can even postpone operators to increase sharing. So it totally depends how you define sharing. We can really change the original semantics to share processing, and later we're going to recover. And that's another way that actually goes beyond the original semantics to save computations. So we don't have theorems for that.
Okay. Thanks again for coming, and thanks again.